Okay, in this problem, we've got a really interesting kind of a real-life issue here. We have a highway road here, and we've got the billboard here. And behind the billboard, hiding right about here, is the police car. And of course, the police car, there's the red siren on the police car, is waiting, and the speeder is going to come along, and here comes the speeder. And the speeder is going at a velocity of 150 kilometers per hour. Man, this guy's really breaking the speed limit. Should we call him a criminal? I don't really know. But here's the interesting thing. The person driving this car is actually texting, so he has no idea about the police. He can't see the police, and he doesn't really notice the police. But the police notice him. And the police driver starts to accelerate. The police driver accelerates at 2.5 meters per second squared as soon as they are in line with each other. So you can call this the start point. And as soon as they're in line with each other, the police car starts to accelerate from rest. So the initial velocity of the police car is 0 meters per second. The question is, how long does it take to catch the speeder? And how far does it take to catch the speeder? How far from this location if we consider this to be 0? So if we kind of if we kind of move this over a bit here and lengthen the road, at some point in the future, we can basically consider, let's pretend, I mean, it's going to be much longer than this distance, but just, I can't really keep scrolling here. But at some point, the police car and the car are going to be at the same location. But the car never changes its velocity. The car's velocity is always 150 kilometers per hour. How do we do this? Well, first of all, let's try and figure out this situation by taking a look at the graph of these two vehicles. Let's take a look at the graph, the dt graph of the car. We're going to call this car, and we're going to call this police. Now, the car is going at a constant velocity. So constant velocity is going to look something like that. It's going to be a straight line in, and it's obviously, if it was flat, the car's position wouldn't be changing. But because it's constant velocity, it's going to be a straight line in the dt graph. However, the police, which we'll do in red, is accelerating. Therefore, initially, since the police starts off at 0, the tangent to the police line is going to be horizontal. But as time goes on, the police officer is eventually going to catch the person right there. Now, the question is, this is what we're trying to find. What time is this? And what position is this? That's what we're trying to find. Those are the two variables which we do not know. However, in order to do this, we have to ask ourselves the question, what condition is met that defines the police car catching the car. And that definition is basically when the police car and the car are at the same location, are at the same position. Okay? Not necessarily, in fact, definitely not at the same velocity. Please get that straight in your head. Sometimes people think, okay, the police car will catch the car when they're traveling the same speed, but this is wrong. Okay? Think if you're on the highway that there's a car ahead of you, and if there's an object ahead of you and you are an object behind it some distance, if you are both traveling at the same velocity, this object will never catch this object. The distance between them will always remain the same if their velocities are the same. So, therefore, that means the police car is definitely going to have to go faster than the car in order to catch him. So the condition for this to be true is actually right on the graph. It means that their positions have to be the same. So let's write down the equations for the position. This is the car, and this is the police. This equation is d equals vt. Why? Because that's constant velocity. On the other hand, the police has a different equation. It has acceleration. However, the initial velocity of the police officer was 0. Therefore, this term can be negated. Hence, we now have, let's put subscripts here, car and police. If we say the position of the car is equal to the position of the police to catch, to be caught, then we can say Vt has got to equal 1/2 at squared. And now we can simply divide both sides by t and do a little bit of algebra. Get rid of the 2 there, put it on this side, and divide by a. And now, in fact, we have our answer. The velocity of the car, that's what this v was 150. Now, we can't use kilometers per hour. We have to change that to meters per second, so we have to divide by 3.6, which will give us meters per second. And we divide by the acceleration of the police officer, which was 2.5 meters per second squared. This ends up giving us an answer of 33.3 seconds. So it takes about, at this location here, that's 33.3 seconds. It takes about a half a minute, just over a half a minute, for the police car to catch the speeder. How far did they go at this time? Well, it's up to you now. You can use either this equation or this equation to calculate how far they've gone. They should both give you the same answer. If we use the simpler one, let's simply go 150 divided by 3.6. That's approximately, I think, 42. And that's going to be in meters per second multiplied by 33.3 seconds. And I think that's going to work out to somewhere, I'm going to write approximately 1,400 meters or 1.4 kilometers. Now I've rounded to like to 2 significant figures here, but that's okay. Now here's the funny thing. Let's not finish this problem, even though it's kind of done. We've got both our answers there, what we were looking for initially, between the delta t and the d. Let's take a look at the Vt graph here. If we take a look at the Vt graph, what is this going to look like? Well, let me draw the car first. So if I draw the car, that's going to be a flat line. That's the velocity of the car, which was 150 divided by 3.6. And let's take this time down. Now, interestingly, we know that the velocity of the police car starts at 0, but do I finish this off here? No, absolutely not. The police officer is not going the same speed when he catches up to him. How fast is he going? Well, here's a hint. Here's a cool little trick you can use that from the concept of area. Now, if you remember, what's the area of this rectangle here? That area is the delta D, isn't it, of the car, because this is the car. Flat horizontal line, because constant slope, constant value. So, and this is 33 seconds here. What's interesting is that you know that the area under the police car's graph has to match the area of the car's graph. But you also know that the graph of the police car has to be a straight line with a slope equal to its acceleration, which is 2.5. But you see, using a little bit of symmetry, I know that at this point, I have to have whatever area I missed here made up for here. And hence, the area underneath this red line is equal to the area covered here. And so what does that tell me about the final velocity of the police car? Well, if you just look at this, you can see the symmetry that the police car is going to be going twice as fast as the speeder. And the speeder, remember here, is going 150. So that means the police car, when he catches up to him, is going to be going 300. Now listen, I don't know what kind of a car the police car is driving, but it better be a Ferrari or a Lamborghini, because I don't think very many vehicles can go that fast. Well, we can also verify this, by the way, just for fun. You can use the equation V final equals AT plus VI, where VI is 0 for the police car. So 2.5 meters per second squared multiplied by 33.3, and sure enough, we're gonna get, hold on, let me turn on my calculator here. 2.5, enter, 33.3 times, and that's gonna be 83.2, but that's in meters per second. And if we wanted to change that, we'd have to multiply that by 3.6, and sure enough, we get 300 kilometers per hour. Hey, I hope you enjoyed this problem. See you next time.